Now steady state condition. The state in which the temperature does not vary with respect to time is called the steady state. Therefore, when steady state exists, the temperature function u of x comma t becomes u of x. That is, u of x comma t is function of x alone. Hence, u of x comma t is function of x alone. Suppose a rod is heated at both the ends by a constant temperature C1 degrees and C2 degrees respectively. After some time, there is no change in the temperature. That means the temperature remains constant in the rod after some time. Hence, there is no change in the temperature if time t varies. That means the temperature function u of x comma t is a function of x alone. It is independent of time t. Such a condition is called steady state condition. So, in the steady state condition, the temperature does not vary with respect to time t. Even though time t varies, there is no change in the temperature in the rod. Such a condition is called steady state condition. So, in the steady state condition, the temperature distribution function u of x comma t is function of x alone. That means it is independent of time t. So, this is the steady state condition. You remember this steady state condition? Now, we are going to solve the heat equation problems in the steady state condition. When the steady state condition prevails, how to find the solution of the one-dimensional heat equation with the boundary conditions. Now, problems on one-dimensional heat equation. With the steady state condition. and zero boundary conditions. Zero boundary conditions after steady state. That means in the unsteady state, zero boundary conditions. Now, problem number 1. Problem number 1. An insulated rod of length L has its ends capital A and capital B maintained at 0 degrees centigrade and 100 degrees centigrade respectively until steady state conditions prevail. If B is suddenly reduced to 0 degrees centigrade and maintained at 0 degrees centigrade, find the temperature U of x comma t at a distance x from capital A and at time t. Solution. So given that in the steady state condition, that means until the steady state condition prevails, the temperature at one end is 0 degrees centigrade and the temperature in the rod at one another end point B is 100 degrees centigrade and a rod of length L. So this is the boundary conditions in the steady state 0 degrees and 100 degrees. Now what is the temperature in the steady state? We have to find out because it does not depends on time. In the steady state, temperature does not vary with respect to time. So therefore we have to find the temperature U of x in the steady state. After that, if B is suddenly reduced to 0 degrees centigrade, now the steady state becomes unsteady state. The steady state is changed into unsteady state here and maintaining the end B is at 0 degrees centigrade. That means in this unsteady state, we have to find the temperature u of x comma t. In the unsteady state, the temperature varies with respect to time t. So we have to find the temperature distribution with respect to time and at any point x. Let the equation for conduction of heat be dou u by dou t equal to c square into dou square u by dou x square. Say this is equation number 1. We know that when steady state condition exists, the temperature function u of x comma t is a function of x alone. That is, u is a function of x alone. U of x comma t becomes u of x. We know that when steady state condition prevails, the temperature function u of x comma t is a function of x alone. Hence, u of x comma t is independent of t. Since in the steady state condition, u is a function of x alone, so the temperature does not vary with respect to time t, since u is independent of t. So since there is no change in the temperature with respect to time t, so this value becomes 0. So u is not a function of t, therefore dou u by dou t is equal to 0. Therefore, c square into dou square u by dou x square equal to 0. By cross multiplication, dou square u by dou x square is equal to 0 by c square. That is a 0. Dou square by dou x square of u is equal to 0. Since dou by dou t of u equal to 0 in the steady state condition. Therefore, dou square u by dou x square, since u is a function of x alone, it becomes d square u by dx square is equal to 0. Since u is a function of x alone, it becomes an ordinary differential equation. Therefore, this can be written as capital d square of u equal to 0, where capital D is equal to d by dx. Therefore, now it is a homogeneous equation. Therefore, auxiliary equation is, we solve in the ordinary differential equations with constant coefficients. auxiliary equation is d square equal to 0, or some textbooks we will use m square is equal to 0. Some of the authors may use m square instead of d, m square equal to 0. Both are same. So therefore auxiliary equation is a d square equal to 0. So therefore that implies d equal to 0 comma 0. The roots are real and equal. So therefore complementary function is its solution. Therefore solution of the equation is of the differential equation is u is equal to, that means u of x is equal to c1 plus c2 x into e to the power of 0x. Since real and equal, c1 plus c2x into e to the power of 0x. E to the power of 0x is 1. Instead of c1 and c2, for our convenience, I am using a plus bx into e to the power of 0x, that is 1. So this is our solution for the differential equation. Say this is equation number 2. I am using the Roman letters. With the boundary conditions from the given problem, the boundary conditions are in the steady state condition. U of 0 at end A is equal to 0 and B U of L is equal to 100 degrees centigrade at another end B. Now applying condition A in equation 2, that means put x equal to 0. Therefore U of 0 is equal to A plus B into 0. Therefore this implies U of 0 is equal to 0 equal to A plus B into 0. Therefore A equal to 0. Substituting A equal to 0 in equation 2, it becomes U of x is equal to Bx. U of x is equal to Bx. Substituting A in equation 2, we get u of x is equal to bx. Say this is equation number 3. Now applying condition B in equation 3, that means put x is equal to L and then substitute u of L is equal to 100 degrees centigrade. Applying condition B in equation 3. U of L is equal to B into L. Here we substituted x is equal to L and x is equal to L. Therefore now we have to substitute u of L is equal to 100. This implies 100 is equal to B into L. Therefore this implies B is equal to 100 by L. So substituting B in equation number 3, Roman number 3. Substituting the value of B in equation 3. U of x is equal to 100 by L into x. X, this is the temperature distribution in the steady state at any point x in the rod. Now we find the temperature distribution in the steady state. After this, B is suddenly reduced to 0 degrees centigrade and maintained at 0 degrees centigrade. Now the steady state is changed into unsteady state and A is already with 0 degrees centigrade. Now B is also reduced to 0 degrees centigrade. Now both the ends are maintained at 0 degrees centigrade. Therefore end conditions are 0 degrees temperature at 0 and at another end point L. That means at A and at B. Now the temperature at the end B is reduced to 0 degrees centigrade. Now at this stage the steady state is changed into unsteady state. That means now the temperature function u of x comma t changes with respect to time t. That means u is a function of x comma t. Hence u is a function of x comma t. Now hence the temperature function u is a function of x comma t. Therefore, the heat flow equation is heat flow equation is dou by dou t of u is equal to c square into dou square u by dou x square. This is one-dimensional heat equation. Now the boundary and initial condition. So here the temperature function in the steady state becomes initial temperature in the rod at time t equal to 0, because now the steady state becomes unsteady state. Now initially what is the temperature in the rod? What is the temperature in the rod before the end B is reduced to 0 degrees? That is 100x by L. So therefore, in the unsteady state, it becomes initial temperature at time t equal to 0. After time t equal to 0, it varies with respect to time t in the unsteady state. Therefore, then we have to find that temperature at any time at any distance x in the rod. From the given problem, we get the following conditions. Condition number 1. At one end A, the temperature u of x comma 0 comma t 0 comma t at x equal to 0 is equal to 0 for all t greater than 0. And second one, u of L comma t at another end B, that is at L, u of L comma t equal to 0 for all t greater than 0. And third one, initial temperature at any point in the rod at a time t equal to 0, that is u of x comma 0, that is 100 by L into x for all 0 less than or equal to x less than or equal to L. This is exactly as in the problem number 1. In the problem number 1. Now, as explained in problem number 1, the correct solution of one-dimensional heat equation satisfying the above conditions is given by u of x comma t equal to a into cos px plus b into sin px into e to the power of minus c square p square t. This is correct solution. Say this is equation number 1 now. So as in the previous problem number 1, the solution is same till the most general solution. That means up to applying the condition number 2. So the solution is same.